Continuous casting and rebar rolling represent two critical stages in modern steel production, combining efficiency, precision, and strength to meet the demands of construction. At facilities such as Sentinel Steel plc, the process begins with scrap steel fed into high-capacity induction furnaces. These furnaces reach temperatures above 1600 degrees Celsius, reducing the metal into a molten state. This glowing liquid steel then flows directly to the continuous casting machine, where it solidifies into long, red-hot billets. The continuous casting method is designed for speed and efficiency, ensuring that molten steel is transformed seamlessly into billets without energy loss. These billets, still radiating heat, move directly into the rolling mill. The movement is fast-paced, ensuring minimal temperature drop and maximum productivity. The billets undergo multiple passes through powerful rolling stands, which compress and elongate them while imparting the strength and durability essential for construction-grade steel. During the rolling process, the billets are gradually reshaped into rebars with their distinctive ribbed profiles. These ribs are crucial, as they enhance the rebar's grip when embedded in concrete, providing reinforcement that modern infrastructure relies upon. Advanced laser measurement systems continuously monitor the dimensions of each bar, guaranteeing adherence to strict international standards. Such precision ensures consistency across thousands of tons of steel produced monthly. Once the rebars achieve the desired size and profile, automated shears cut them into standard lengths. Workers then bundle the finished bars for distribution to construction sites. Each stage of the process, from furnace to final bundle, combines cutting-edge technology with human oversight, creating a blend of industrial intensity and craftsmanship. The continuous casting and rolling process not only maximizes energy efficiency but also supports rapid construction growth. At Sentinel Steel, this technology helps supply Ethiopia's expanding skyline with the structural backbone it needs. Every glowing billet, every ribbed rebar, reflects both the power of modern steelmaking and the pride of the people who produce it. The hot-dip galvanizing automatic system installed by EstGal in 2018 at Avrasya Galvaniz, Ankara, is a state-of-the-art facility designed for high-efficiency, durability, and environmental compliance. Built around a robust galvanizing kettle measuring 1.9 x 13 x 3.5 meters, the system is capable of handling large and heavy steel structures with precision. With a fully automated process flow, the plant ensures consistent coating quality, reduced human error, and enhanced productivity. Its total galvanizing capacity reaches 74,000 tons per year, making it suitable for both domestic and international industrial demands. At the heart of the system lies the Hasco furnace system, which delivers efficient heating and uniform temperature distribution across the kettle. The furnace operates with a capacity of 21 tons per hour, ensuring fast and reliable production cycles. The zinc enclosure and furnace kettle integration guarantee energy savings and safe operation. Supporting units such as hydraulic lifting stations, transfer shuttles, and automated conveyors streamline the handling of steel parts, from pretreatment to galvanizing and drying. The pretreatment section is fully enclosed, incorporating pretreatment tanks, enclosures, and a waste gas system to meet environmental and safety standards. Surface cleaning and fluxing are carried out in a controlled atmosphere, followed by drying in a 70 degrees Celsius dryer room. The system also includes a flux regeneration unit, ensuring minimal chemical consumption and consistent galvanizing quality. Environmental responsibility is reinforced through the inclusion of a baghouse filter and scrubber system, which effectively capture and neutralize emissions, maintaining clean air within and outside the facility. The dryer lids, heating systems, and zinc enclosure further minimize heat loss and optimize energy efficiency. Reheating furnace uniformly heats billets for optimal rolling efficiency. Furnace exit water descaler removes billet surface scale effectively. The roughing mill consists of 6 Red Ring Series 5 stands, designed for the initial rolling stage, where reheated billets are reduced in size and shaped for further processing. These stands provide high rigidity, durability, and precise control, ensuring consistent deformation of the billet. The roughing stage sets accurate geometry, distributes material evenly, and prepares billets for the intermediate rolling mills. The insulated roller table minimizes heat loss, maintaining billet temperature during transfer from the furnace to the roughing mill. Pinch roll guides billets, shear cuts lengths for precise rolling. The first intermediate mill, with 6 Red Ring Series 5 stands, enables quick stand changes, ensuring flexibility, reduced downtime, and efficient rolling. Crop and cobble shear removes defects, ensuring smooth rolling continuity. The second intermediate mill features 6 Red Ring Series 5 stands, equipped with an inline quick stand change system. This setup ensures precise reduction of billet size, rapid adaptation to production needs, minimized downtime, and high efficiency while maintaining consistent product quality. Pinch roll, shear, and uplooper ensure smooth billet handling. Bar size gauge measures dimensions, ensuring accuracy and quality control. The shear arrangement enables precise cutting of bars to required lengths, improving dimensional accuracy, operational efficiency, and product quality consistency. Approach table and brake slide align, control, and stabilize bars. Cooling bed uniformly cools rolled bars, preventing distortion and defects. Cutoff machines with 3-1 800mm disc saws perform head cutting and divide bars into precise commercial lengths for further processing. Chain transfer moves finished bars efficiently for bundling and dispatch. Bar counting ensures accurate tally of finished bars, supporting precise bundling, inventory management, quality assurance, and smooth downstream handling and logistics. The coking process transforms coal into coke, a crucial fuel and reducing agent for the blast furnace. Coal is heated in airtight ovens at 1001, 200 degrees Celsius without oxygen, driving off volatile compounds like tar, gas, and water. This leaves behind a strong, porous carbon-rich material that burns efficiently and supports iron ore in smelting. The steelmaking process begins by transferring molten iron, known as hot metal, from the blast furnace into a converter furnace. Here, a jet of pure oxygen is blown into the molten iron, initiating oxidation that removes impurities such as carbon, sulfur, silicon, and phosphorus. This chemical reaction reduces unwanted elements, lowers carbon content, and generates intense heat. The result is crude steel with improved strength, durability, and controlled composition for further refining and casting. Rolling compresses and elongates heated crude steel between rotating rollers, reducing thickness and shaping it into sheets, plates, or structural forms. The tailor-welded blank shop welds different steel sheets into customized blanks, enabling precise rolling for lightweight, high-strength automotive components. The Automotive Steel Plate Processing R&D Center develops advanced steels and forming technologies, enhancing vehicle safety, performance, and lightweight design efficiency. The scrapyard is the starting point of production, where high-grade scrap, pig iron, and hot briquetted iron, HBI, are stored, sorted, and blended. Each customer order determines the precise metallic mix, ensuring consistent quality and optimal steelmaking efficiency. The melt shop uses giant clamshell buckets and overhead cranes to charge scrap into electric arc furnaces, initiating the steelmaking process. Electric arc furnaces, EAFs, are the core of the steelmaking operation, transforming scrap and metallic charge into molten steel. Massive graphite electrodes are lowered into the furnace, generating powerful electric arcs that produce temperatures near 3,000 degrees Fahrenheit. This intense heat rapidly melts the metallic mix, creating a molten bath in less than 40 minutes. The process is highly flexible, allowing different scrap compositions and alloy additions depending on customer specifications. Once fully melted, the furnace is tapped, and the glowing steel flows into a ladle for refining. EAFs provide efficiency, environmental benefits, and consistent quality in modern steel production. Ladle metallurgy furnaces, LMFs, refine molten steel after tapping, adjusting chemistry with alloy additions, controlling temperature, and removing impurities, ensuring precise composition, cleanliness, and consistency before casting into slabs. The slab caster solidifies molten steel into continuous thin slabs through a controlled cooling process. Molten metal flows from the ladle into a tundish, then into a water-cooled copper mold that rapidly forms a semi-solid shell. The strand descends vertically, gradually solidifying as it passes through rollers and sprays, before being sheared to length, creating uniform slabs ready for reheating. Tunnel furnaces reheat cast slabs to a uniform rolling temperature of around 1900 degrees Fahrenheit. Stretching nearly 3 football fields, they ensure consistency, efficiency, and proper metallurgical conditions before hot rolling. The 6-stand hot mill reduces thick steel slabs into thin strips with precise dimensions and surface quality. As the reheated slab enters, it passes through 6 powerful rolling stands, each progressively reducing thickness while controlling shape and uniformity. Starting at 2.5 inches, slabs can be reduced to as thin as 0.054 inches. The process ensures strength, flexibility, and versatility, producing coils suited for automotive, construction, pipe, and appliance applications. Forge welding a small anchor is a traditional blacksmithing technique that combines skill, precision, and an understanding of both material and heat. The process involves heating separate pieces of wrought iron or mild steel until they reach a near molten state, then hammering them together so the surfaces fuse into a single, solid mass. This method was historically important in anchor making, particularly before modern arc and gas welding methods became common. When forging a small anchor, the smith typically begins by shaping the individual components, the shank, arms, and flukes. Each piece must be carefully prepared with clean surfaces, as impurities like scale or dirt can weaken the weld. The parts are then heated in a forge until they reach a bright yellow to near white heat, around 1,200 to 1,300 degrees Celsius. At this temperature, the metal becomes plastic and sticky, ready for welding. A flux such as sand or borax is often sprinkled on the surfaces to prevent oxidation and to promote a clean bond. The welding itself requires quick, decisive hammer blows. The smith brings the heated components from the forge and positions them precisely, then strikes firmly to drive out any remaining flux and scale while ensuring the metals fuse. For an anchor, the main welds are usually between the shank and arms, where strength is most critical. Multiple heats may be necessary, especially for thicker stock, as the weld must be consolidated gradually to avoid cold shuts or cracks. After the welds are secure, the anchor is reheated and shaped to its final form. The flukes are drawn out and spread, the shank straightened, and the crown blended smoothly to ensure both strength and symmetry. Finally, the eye or ring at the top of the shank is forged, allowing the anchor to be secured with a chain or rope. Forge welding a small anchor demonstrates both the functional and artistic aspects of blacksmithing. It demands careful control of heat, timing, and hammering technique, but when done well, it produces a tool that is not only durable, but also carries the character of traditional craftsmanship. This method, though largely replaced by modern fabrication, remains a valuable skill for historical reproduction and traditional smithing practice. High-quality raw materials are essential for cast iron production, including pig iron, steel scrap, recycled cast iron, and alloying elements, which are carefully selected to ensure durability, resistance, and consistent product performance. In the casting stage, molten iron is poured into prepared molds under controlled conditions, ensuring uniform filling. This process shapes the product's structure, providing strength, durability, and the precise form required for further processing. Molds are carefully designed and produced using high-quality sand and resins, ensuring precise dimensions and smooth surfaces. This stage is crucial, as mold accuracy directly affects the product's final shape, surface finish, and structural integrity during the casting process. Molten iron is carefully poured into the mold cavity, ensuring complete filling without air pockets to achieve accurate shapes. After solidification, the mold is broken apart to release the cast piece. This process requires precision to avoid damaging the product, ensuring the cast iron retains its intended shape, structural integrity, and surface quality for the next production stages. Excess material and irregularities are removed, followed by precision machining to achieve accurate dimensions and smooth, functional surfaces. The cast piece undergoes initial inspections, checking dimensions, surface finish, and structural integrity to ensure compliance with production standards. A protective enamel coating is applied to the cast surface, providing adhesion, durability, and a smooth base for subsequent finishing layers. A final enamel layer enhances durability, color, and finish. The company logo is permanently applied to each product, ensuring brand identity, authenticity, and traceability while maintaining a professional, consistent appearance. Each finished product undergoes rigorous testing, including dimensional checks, surface inspection, and durability assessments, ensuring it meets strict quality standards before packaging and delivery to customers. The mold is precisely designed and crafted using durable materials to ensure accuracy, consistency, and reliability in faucet production. Molten metal is carefully poured into the prepared mold, filling every cavity to create the faucet's basic shape and structure. Once the metal solidifies, the mold is carefully removed to release the newly formed faucet piece. Excess material and feeding channels are trimmed away through precise cutting, ensuring the component is clean and ready for further processing. This step guarantees accuracy in shape and prepares the faucet for machining. During machining, specialized tools shape and refine the faucet component with high precision. Holes, threads, and surfaces are accurately finished to meet exact specifications. This process ensures functionality, smooth assembly, and durability before moving forward to quality control and finishing. Each faucet undergoes strict inspections to guarantee precision and reliability. Grinding smooths rough surfaces, removes imperfections, and prepares the faucet body for polishing, ensuring a flawless finish and consistent quality. Polishing enhances the faucet's surface by creating a smooth, shiny finish, improving both appearance and durability before final assembly and packaging.